universe is calling you. The universe is calling me. It speaks both day and night. It's full of dark and light. And I've heard others call from light years away. And they're real, and they're here. Space and time are instantly clear. Planets spin, grids in place. We can travel through space, fields and forms, math and voids. It all sings with one voice. It's boundaries set, foundations laid. Sound was heard, matter made. Solar systems from afar. Names and numbers for the stars. And I've heard others call from light years away. And they're real, and they're here. Space and time are instantly clear. Planets spin, grids in place. We can travel through space. It's the Lord's.
Hey, welcome everybody to Skytour Livestream. I am your host with the most, I guess, the passport to the stars through Skytour Livestream. And we have with us tonight, of course, Daryl. How you doing, Daryl? How's it going?
I'm here to see Santino D'Antonio. You're supposed to say, he's waiting for you at the lounge, sir.
That's right. Santino D'Antonio, the nemesis in John Wick 4, I believe. Is that correct?
Mark, you've got a... that was John Wick 2.
Oh, okay.
Terrible echo.
Okay, well, it's probably different now. All right? Can you hear me? I just cut the roll off. Okay, hold on.
Testing.
Say it again.
Testing.
No, I hear you. You hear me okay?
Still got an echo.
Yeah, okay. I'm wondering why. I have my settings where they should be. Well, while we're waiting to figure this out, no one listening has an echo from me, so clearly it's between you and I with the Skype issue. Let me try something else. How about now? Do you hear an echo now?
I did. I don't know about now.
Okay, well, do you hear it now?
Yes, I do.
Okay. All right. Not sure where that comes from. Because I've got things set up the way they're supposed to be. Anyway.
Testing, 1, 2, 3.
Well, everybody hears you saying that, so they know you're... I hear you fine. And no one out there in the stream hears you echoing at all, or me. So, like I said, it's got to do with something with our Skype here.
I still hear it.
Okay, one thing you can try is go into your Skype, go into your audio settings, you go down to speakers, and see what you got there.
Yes.
Okay, what have you got for your speaker settings?
Yeti stereo microphone.
That's the microphone. What about speakers?
Yes, speakers, Yeti stereo microphone.
What other selections do you have?
Default communications device, Dell display audio, and speakers, headphones, Realtek audio. Now it was on. It was on speakers, Realtek audio when my speakers were still working when I was on headphones.
And you changed it.
I changed it to Yeti stereo microphone.
Okay, change it back to the Realtek and just turn down your external speakers, and let's see if that works. So, if you're talking...
I did.
You did? Can you hear me, though?
I still hear you echoing.
Okay.
I'm echoing also.
Okay.
Yes, I can hear you, but there's an echo.
Okay.
The echo is coming over the speakers.
All right, well... Very strange. Not sure what to do about that, because this is the same setup that we've been using successfully for the longest time. Let me try something here. Anyway, what kind of echo is it actually? Is it like a half second or like a very, very tight echo?
It's several seconds later.
Several seconds.
Like 3 or 4 seconds.
Oh, that's terrible.
Uh-huh.
All right. Well, that's something that I hate to say it, but I'm wondering if maybe...
Oh, duh. Hang on. Okay, I bet we have no echo now.
And how is it working?
Sounds good so far. Hello, everybody. Can you hear me okay?
So, yeah, they never stopped hearing you okay. And they never stopped hearing me okay. So, what happened?
I'm an idiot. I didn't mute the YouTube page. I'm an idiot. Sorry.
Okay.
Hello, everybody.
Everybody can collectively say Daryl's an idiot tonight. It might be your one and only chance, so don't waste it.
Yeah.
That's no problem. Okay, good. So anyway, while we're waiting here to let this come in, I'll tell you more about this in a second. I want to say hello to Renee Cruz. She was the first one here. Hi, Renee. Tim F. Woohoo! What's happening, brother? Nice to see you. Slap Astronomy is here. How you doing, Slap? I'd be interested to know what SLAP stands for, and love to talk to you. And let's see, we got Michael Hedrick. How you doing, brother? Good to see you. Hey, brother. And Sam S. is with us. Nice to see you as well. Mind Forked. I know her. Okay. By the way, I've been invited to Roswell again, and I'll be at Contact in the Desert again. So I don't know if you're going to go to any of those two places, but if so, I'll be there, and we'll see each other. Daisy and Zoe, hi guys. How's Lane? Has Lane joined you lately? Calabos is here. Nice to see you, brother. Nice to see you. Alicia is with us. Hi, Alicia. Is Darlene with you? So I think that we're gonna have a good night tonight. I'm gonna share with you some new technology that we're using. It's a piece of the product here that we're using that we've added in. It's very windy out there right now. In fact, it's so windy that we're getting gusts of 20 to 25 miles per hour, anywhere between 11 and 20 miles an hour. But you notice we're stacking here. This is the Veil Nebula, Eastern Veil, one half of this beautiful, roughly spherical supernova remnant that's expanding away from the pulsar at the center of this explosion that occurred, I think it was like 8,000 years ago, something like that. And this screen, though, you notice the stars are pretty round, and the reason is because I've added a new filter. Okay, and the filter is something called the full width half maximum filter. What does that mean? Well, it means that if the star blobs are too big or elongated, it rejects it from the stack. Okay, and only those that meet my minimum can be stacked. So far, you can see we've literally stacked 39, but we rejected 57. Okay, this is the test image I put up there just before we started. So what happens is we get really good images even if we've got turbulent weather out there and the sky is turbulent, right? Really cool. Now the other thing too I wanted to mention is that hey, C&D boy is with us as well. Good to see you. The one thing I wanted to mention as well is that this number here can be lowered, and I can type in a number I want. And so, like, for instance, you can see that the good ones are 7.27, 7.84. And if I really wanted to be picky, I could drop this down to 7.5 or something like that. And now the star image won't be allowed to bloat as much. In fact, if I wanted perfect images, I could lower that down to a minimum, a bare minimum that's within reason. And so that bare minimum right now is it could be a lot higher. A lot lower than 8.05, because you can see that even at 8.05 with 20 mile an hour winds out there, okay, in gusts, you can still see that our stars are slightly elongated. I didn't want to reject every single image, all right? I wanted to have some images to show you. But that's what we're seeing here. We're seeing this full width half maximum filter operating, and it's just really, really nice. So what it means is we're never going to end up with ruined stacks anymore. You know how sometimes we get these beautiful stacks and all of a sudden something happens and then the next frame is, oh no, the stars are elongated. Never again. So we're going to be able to do this from now on. It's really cool, and I really like it. And we're going to be adding other features as well moving forward. Okay. So this is the Eastern Veil, right? And, if you're interested in who we are, well, up top there, you can see it's skytourlive.org. And over on the right, if you're interested in some Christmas gifts, go to Skytour Shop on Etsy. Search for Skytour Shop. And we've got like 50 different mugs and blankets and duffel bags and shoes that are all emblazoned with our imagery on them, and they look stunning. And there's a lot of people that A lot of people that have purchased products already up there. It all goes to support us. It doesn't go in my pocket. It goes and supports Skytour Livestream. So I think that's really cool. If you guys can help out that way, that's great. And again, Christmas is coming, so why not, right? So we'll go back to our histogram view here. Now, as I said, the moon is still out. We have just, it's a pretty bright moon. So our sky is pretty bright from the moonlight, but we can drop that out and reject the moonlight and allow us to see just our beautiful objects here. And this is just gorgeous, I tell you. It looks so pretty.
I read something interesting about the moon a day or two ago. So the Sky and Telescope, their weekly what's up in the sky thing.
Yeah.
The planet Saturn is at quadrature. That is, it's at 90 degrees from the sun.
Mm-hmm.
And so it's halfway between opposition and being at superior conjunction behind the sun now. And it may be tomorrow, since the moon is almost at first quarter tonight. If it's tomorrow night, the moon will be right close to Saturn, because first quarter always happens 90 degrees from the sun.
Mm-hmm.
Therefore, you're going to see Saturn and the moon close together in the sky.
And as Daryl states that, I'll bring up our stellarium here, and let's actually go and look at that. And you'll see that. Let me just show you back here. Let's back out a little bit. Cross the pole, come back this way. We're going to be visiting this area later on tonight, actually.
Saturn's in...
I know where it is. We got it right here. Coming right
yep.
up. I'm moving it. I'm just
Aquarius, I believe.
Yeah, I'm just trying to move it in a way that doesn't make it go wild. It's coming up. There it is.
Right.
So here's the moon, and there's Saturn, as Daryl said. So you can see that he's not lying. He's telling you the truth. There's Saturn. There's the moon.
And by tomorrow night, the moon will have moved over about 13 degrees to the left.
Yep.
Probably be a little bit past Saturn by tomorrow night.
I think so. Yep. Very nice. Okay, so...
anyway.
No, it's all good. It's very good. So, back to our object at hand. Okay, this is the Eastern Veil. It's part of this complex here. This is an entire supernova complex. And this supernova complex, this occurred, I believe it was like 8,000 years ago. And it's in the center here somewhere is the former progenitor star that obliterated itself. And when it did, the stuff's just expanding out from the center of the explosion, some toward you, some away from you, and some to the sides and all around. Okay, kind of in a spherical pattern. And so we're seeing this in a kind of a perspective of it's 2D projected on our sky. We can't really see it in the true nature of how it is. We don't see the parts that are closest to us. We can't see the parts that are farthest. It's possible, for instance, when we look at this, all right, if we go back to our screen here, all right, when we look at this screen here, it's possible that this part here is actually a combination of stuff that's going away from us and coming toward us, okay? So there could be stuff back here, and we can see it curling around toward the front. Because, again, the universe is in 3D, but we're seeing it projected on the sky, so it looks like it's flat on the sky. It's anything but flat. The universe is not only three-dimensional, of course, but it's a time machine. So I think that's something else to consider here. So
Can you back out a little bit?
Yeah.
See his whole profile there?
Yeah, when I do the stack, you can't see the bottom. Yeah, but there's the whole profile. I say profile, as Daryl was probably about to tell you, doesn't this look like a person's face? Here's an upper lip. Here's a lower lip. Here's a chin. Right? Here's a nose.
Yeah.
Right?
We were saying earlier, sometimes we call that Alfred Hitchcock, but
Yeah.
that's not Alfred Hitchcock. The shape of the face is wrong,
And so is
and the nose
the
is
nose.
wrong.
Yeah, yeah. And the
And I
lips.
can't think of who it is. Like a Bond bad guy or something. He's got an evil looking nose,
Yeah.
where Hitchcock had a round nose.
Yeah. Yeah, that's true.
Any suggestions?
Yeah, if you think who that might be. Yeah, it's like, do you expect me to talk? No, Mr. Bond, I expect you to die.
Yep.
That guy. He might fit that profile. Yeah,
All right, Goldfinger.
that's it. Say hi to Bonnie, Anahata 77, and Cindy Murphy. Hi guys, how are you? Thanks, Calabos says please like and share. Yeah, please do that. I mean, let's be. I'm just speaking honestly. There really isn't anyone out there doing what we're doing. Nothing like this exists on YouTube. You don't have a live telescope with an astronomer who can lead you through different objects and share the nature of these different objects with you like this. This is very, very different, and Daryl's input is very important because, as an observational astronomer, he can tell you about he can tell you what a syzygy is, for instance. Now, when you get into astronomy, at my end of things, I talk about the nature and the physics of what's going on in here. Okay, Daryl can tell you where it is, how it, and basically how it relates to us in other ways. So you get a full rounded picture, I believe, between the two of us on this. So it's pretty cool. Syzygy is his favorite word, by the way.
Yeah, I thought of getting a license plate to say syzygy.
Do you have enough letters in Colorado?
Yeah, that's 6 letters, so that'll work.
Yeah.
SYZYGY, syzygy.
Yeah.
It's when 3 astronomical objects form a straight line in space, like during a lunar or a solar eclipse, or during a
Planetary alignment,
an opposition or something like that.
or a planetary alignment toward the sun, which is rare but can occur. Daisy and Zoe Amethyst say, Cousin Lane just walked in the door with cookies. Virtual share. Only if I know what kind they are, Daisy. I want to know what kind of cookies you got. And whether I'm talking to Daisy or Zoe or both. Christopher Thompson asked, how's Polaris looking tonight? Polaris is looking the way it always looks. It's just a nice big star. And if we wanted to look at Polaris, if you look right here, this axis of the telescope right here, right there, that right there, that's the polar axis. So the telescope will be pointing that way, right at Polaris. And we don't typically do that. I actually tried to do a polar alignment, which I didn't need to do. I just wanted to do it as a, just a process when I was there a few weeks ago. And I ended up pulling on some cables that I didn't want to pull on. So I had to take care of that. Cable management's huge. Because if you look in the side there, you'll see there's a huge braid of cables that are dangling from the telescope with freedom to move around. Because you need that, because the telescope points every which way. And you've got like 10 or so cables going to the telescope, from focusing to other top-mounted systems to the telescope itself, and the focusing system. There's a lot going on there, so we encase a lot of cables in what's called a pull member, so that in case anything does get tugged, the pull member takes the stress and the cables don't. So there we go. Oh, you know what? I wasn't going to keep this, but I will, because it really is looking pretty. You can always do something with a pretty image. And by the way, I figured out the technology to actually take stars that are slightly elongated and fix them. So I'd rather take the image correctly to begin with. but I just wanted to mention that that's something else that's possible now. Okay, so we're going to save this. Save it exactly as seen. Okay. Now, like I said, it's very windy out there. And so what we'll do, just to give you an idea, what the moon looks like. Keep in mind that our telescope is really, it's a wide field system. It's not meant for doing close-up stuff. Hi, Izabela. Isabella's here.
Hi, Izabela.
Yeah. And so there you can see. The other thing I did was I implemented a master dark frame calculation. That's the wind that you see pushing the telescope around right now. It's a giant flag sticking up right here. See it? That big old flag sticking up right there, and it just like, catches the wind and gets buffeted. But I implemented what's called a master dark frame. So every single frame that's taken, the noise of the sensor is subtracted, and every sensor has noise. So it's an average of a number of frames that are removed. So it doesn't get all of it, but it removes a good deal of it. And that's why the images look better right from the very start. Instead of having like a brightness of a sensor, there's a bright amplifier noise over here that's no longer there. I mean, it's there on longer exposures, but I kind of took an average. Anyway, let's go here. All right. And the idea is to stay far enough away from the moon so that we can still have some good fun. But I do want to actually take it to the moon anyway, if we can still get there. I'd like to show you the moon in here so you can get an idea how big our field is. It was there. There it is. Okay, so now we're going to have to stop down all our settings here pretty quick, which we'll do. All right, so here we go. We're going to say Control 1. Notice, watch the telescope now. There it goes. And it's going to kind of point toward me here in a bit. All right, it's doing it right now. Then we come back in here, and the screen's going to get pretty bright as we get closer to the moon. And it won't look like much of anything until I do this. Now we have it so bright that you can actually see stars near the moon, right? And satellites, as you can tell. The one just flew by. Telescope is still trying to figure out how to guide from this position. But we'll move over now. Move to the east a little bit. And you can see the non-sunlit side of the moon. So you'll say, well, how come we can see this side of the moon? And it's actually because from the moon's perspective, half the Earth is illuminated. And that illuminated big blue marble is actually casting a glow on the lunar surface, and that's why we see it here. That's called Earth shine. Look, there's a star right there. Star right there. Now, in order to see this better, what we do is we turn down our sensitivity on our sensor to 0. Right? And that's still not enough because it's a very sensitive sensor. So we can actually go down to maybe 75 milliseconds and then work up from there. Okay, gotta work down a little more. How about that? So we can come down. This gives you an idea how big our field is, though. It's literally 1.5 degrees across by 1 degree tall. There we go. So there's our moon. So basically, if we were to move the moon to the bottom of our field here, okay. Okay, now you can see that if you put another moon above it, it would just get to the top. Let me make it a little more obvious here. keep in mind that all the signals I'm sending are going 2,500 miles because I'm running this from Connecticut, and the telescope is out in the Arizona desert. And Starlink is the reason we can do this. We just upgraded at my end here in our bunker. We upgraded to gigabit internet, so we have 1 billion megabits per second up and 1 billion megabits per second down. It's the same speed up and down. And believe it or not, that costs less than the previous Comcast service we had. So it's really, really crazy. So you can see that if you double this, it'll be just about as tall. So it's about 1 degree by 1.5 degrees. So the moon goes out to about here. All right. Of course, we can see that by just doing this, by increasing the exposure, and you'll get to see the other half of the moon illuminated. Okay, you can barely see it there. Turn the gain up. And if I actually blow it up, then you can see it right there. So you can see that you can get 1 and about 1/2 of one across. So it's 1.5 degrees by 1 degree. That's our field of view. This is with the new camera. With the previous camera, we had just over 2 degrees by 1.5 degrees. So it's actually a tighter field of view, and it has many more pixels in that field of view, meaning more detail can be seen in the areas that we photograph. And it's been paying dividends like you cannot believe. Some of the photos we've taken are just like astonishing, the way the detail it looks. It's so different from what it was before. Wouldn't you say that?
When we see the dark side of the moon dimly glowing like that, that's from reflected Earth light.
Yeah.
If you were standing on the moon looking up at Earth, it would be, it's not quite first quarter there. From the moon's point of view, we would be a little more than half lit on Earth and lit on the other side. Like to our left, I guess, if we're on the moon.
Yep. Okay, so let's go back now to Stellarium here. Let's see. I want to take us back up north, get away from the moon as far as we can. And we can go up here. I'm going to take us up to Deneb right now. And then from there, we'll use that as a jumping off place. There goes the telescope. Yay, it's going to go looking a little bit toward me this way a little bit. There it goes. You can see up above, it's actually doing that. And now we're going to go and bring in our full... Alright, 200, and then maxed out. Alright, and that should be Deneb. I can't really tell if it is. Let's find out. Alright, let's go here. And we'll know in a heartbeat. Alright, so we're going to go now and look at this interesting object right near this star. And kind of looks right. But let's go to our 1 second view. Alright. There we are. Okay. And now we're going to do well, again, it's windy, but let's try this. Let's see if we can do it. We're going to do a 15-second shot. And in that 15-second shot, we're going to go into our live stack here. And we're going to, from within our live stack, we'll clear the previous. We're going to go into our tailor-made piece right here, the full width half maximum. And let's see if the first shot comes in. It may not. Yeah, see, it's windy, so we got to let it calm down up there.
Mark, when you have a moment, Michael Hedrick has a question for you.
Okay, he says, could you talk about lenses for a moment? How they're made, how they bend light, anything, optics. Well, if you want to talk about the physics of optical paths, Daryl is equally qualified for that because he engineered the collimation and engineering of lasers for most of his life. So he is also quite well versed in optical paths. He could tell you about Snell's law and all kinds of physics that has to do with the way light refracts and bends in different substances, and how it changes speed in different substances as it enters it. So there is a lot of physics in there, and it's really hard to tell you. I mean, lenses are ground. Let's be honest. Okay, you have a clear blank, and then you grind the lenses. Nowadays, it's done by machines that can actually grind very, very precisely to get the lenses to a particular shape. And they could be convex, they could be concave, okay? They could be plano-convex, where it's flat on one side and curved on the other, and so forth. So there's a lot of different ways and a lot of different considerations for how lenses are made. Oh, look at that. We're up here in the middle of the North American Nebula. We're going to get rid of you. All right. Look at that. I know where we are. We're a little bit far north right now. But, Daryl, if you want to tackle that and answer, feel free. I don't have any problem with that.
Oh, that's a huge subject.
It sure is. I'd have to teach you about Snell's law. Not you, but, at the very beginning. I mean, you talk about how lenses actually work, but actually how they're made, though. You can talk about the molten states and stuff like that, and how they're actually cooled and ground, if you want.
I hardly know where to start. Lenses, as Mark said, I mean, consider you take a flat piece of glass and you shine light through it. Well, the light goes through, but it doesn't change its character. If you curve those surfaces, you can make the light, the angle of reflection always equals the angle of refraction. Is that right? Angle of incidence equals angle of reflection.
Yes.
So if you put a curve on the one side of the glass, the light's not going to intersect at a right angle. It's going to intersect at a given angle, and it's going to leave at that same angle. And when you can do that, you can move the light around and make, this is oversimplifying, but you can make things get bigger. If you have a negative curvature, that is concave, you can make the object in the lens get smaller. Again, this is vastly oversimplifying. Oh God.
Well, you can talk about ray tracing, right? If we have a convex lens, you think of light hitting and then refracting at a certain angle, and based on the curvature of the lens, the light's going to go a certain way. And so light that comes in, the convex lens will tend to enlarge it. This is why magnifying glasses are convex on both sides.
Yeah.
Okay? And again, I'd have to show you an example, and I'd have to do a little lab with it to kind of do. I used to do a lens lab. I used to teach lens optics, actually, and I did it for everything from third graders all the way to college. And they were equally enthralled. Everybody loves to learn about lenses. And when you set up what's called an optical bench, which is something Daryl's very familiar with, having worked with lasers, an optical bench is an extremely precise setup that would hold lenses a certain way, light sources a certain way, And then you could measure every single element, every single feature of the optical bench, the distance from the lens to the source, the distance from that lens now to another lens, and so forth. The types of lenses, specific ratios of lenses, and get an expected result based on a calculation that you can do. It's such a deep subject that it's literally beyond what we can talk about in here and literally get across in a reasonable way.
Yeah, I will say this. With lenses, some of the pioneers were, what's his name? Anton von Leeuwenhoek or something like that.
Yeah, Leeuwenhoek, yeah.
He invented the microscope.
Yeah.
And a guy named Hans Lippershey started playing with magnifying lenses. So instead of looking at things on the tiny scale, he got the idea to look at things on the big scale.
Mm-hmm.
Galileo took Lippershey's ideas, I guess, or whoever really invented the lens. He was the first to think up the idea of building a telescope with them.
Yep.
To look at far-off objects and make them look bigger in the eyepiece, in the lens. And the other whole side of the coin there is not lenses, it's mirrors.
Yeah.
And Isaac Newton was the first guy to use mirrors to make a telescope. That's why they're called Newtonian telescopes.
Mm-hmm.
And nowadays, you know, like Marc's telescope, it's got mirrors in it. It's got lenses in it. The front corrector plate is sort of a basic weak lens that's got a big mirror in the back, and they can make the light make the object appear larger, like we're doing here. That's the whole idea of a telescope. It's a huge subject, as Marc said, and as I said. Just look up optics and start from there.
Yeah.
It'll tell you more than you ever wanted to know.
Yeah, that's right. Okay, we're taking a picture of the North American nebula, but we're doing it like the Gulf of Mexico. This would be Florida here. Okay, this is the Gulf of Mexico. This is Mexico, and this is what's called the Cygnus Wall. It's a concentration of dust and gas here. The red is the ionized hydrogen. This black stuff is actually here in the foreground, and this other stuff glowing is behind it. So this black stuff in the foreground here is obscuring what's behind it. So that's how this works. And as you can see, we have one frame we've stacked. We've ignored 3 so far. I have the numbers set to 8.05, so we'll get a reasonable image here. And we'll just wait it out and wait for us to get one that's actually to stack with. I want to talk about a question that came from Cygnus in the chat. He asked specifically, STS-75, a shuttle launch, there was a tether incident. And he said it had something to do with the lenses rather than a bunch of discs flying around the tether. First, let me acquaint people with the incident. And yes, I'm somewhat of an expert on that one. I'll tell you why. Because the Discovery Channel had me go to Dallas to recreate the tether incident on camera. And I did. And there was a lot of disappointed people that thought they were going to see UFOs, and instead they didn't. They saw ice particles. Now, what does that mean? First of all, the incident. There was a tether on the STS-75. I believe it was STS-75. Do you have that number right? Check on that. And there was a satellite with a tether coming out of the shuttle, and that tether was supposed to measure electrical currents. And what ended up happening was the tether snapped. And when it snapped, it ended up moving up to 75 miles away from the shuttle, but it was still brightly visible because both the shuttle and the tether were in bright sunlight with stark black background. And then all of a sudden you saw these particles flying around, and it looked like they were flying behind the tether. And they were big donuts with a notch cut out of them. And those donuts, like as I said, they appear to be flying behind the tether. Now, they said, look, those are 2-mile wide UFOs. No lie, I'm telling you, that's what they said. And they said, prove it isn't. And I said, okay. I believe that alien life has made it here. I mean, there's no reason it can't. But in this particular case, it's not true. I do believe I know exactly how this happened, and I'll make it happen. I'll recreate it. So here's how it works. Tether's in the distance. It's bright, bright white, and it's overexposed on the video image. It's a low light camera. Okay, so the image of this long, thin tether is as bright white as it can get. What's that mean? It means that anything that flies by it will appear to be going behind it. Because if it could go in front of it, it means that the brightness of the tether wouldn't overwhelm it, but the brightness of the tether was huge. Okay, and we got a second one, yay! And the object would be able to be seen in front of it if it was big enough and bright enough on its own. Well, the problem was the things that were being that looked like they were passing behind the tether were actually way up in front of the tether and out of focus. Okay, this means that a tiny dot would become a large donut shape. Why a donut? For the same reason that when we defocus our telescope here, the stars look like donuts. It's a system that has a secondary obstruction. You have a primary mirror at the bottom, and you go to the top, and as Daryl said, there's a corrector plate of glass, circular plate of glass. In the middle of that plate of glass is another round mirror. Light goes down to the bottom, hits the primary mirror, comes up and hits that secondary mirror, then gets reflected again down to the center of the mirror in the back where there's a hole. And then that comes out to your camera or your eyepiece. All right? We're doing it a little differently, but we still have a obstruction. Okay? Well, that obstruction then in the telescope that was shooting this tether incident was also there. It was a Maksutov little telephoto lens attached to a camera. Those can fly in space. In fact, the shuttle had them on board for flights regularly. So you just sign one out, take it in, connect it to your camera, and go shooting. And that little Maksutov has a secondary mirror obstruction, and that's what happens when you go out of focus. You see the donut, and that's what we saw. Okay, and when it's out of focus, it's also much less bright. So, because it was much less bright, we found that the object always looked like it was passing behind the relatively brighter tether. And so I set up objects, and I had them floating in front of the tether, which was 40 feet away across this studio at this facility in Dallas. And they ran it with the camera, and these objects floated as little donuts in front of the tether to your eyes, but they were seen as going behind the tether on the video. But they weren't really. It was all an illusion. And there were a lot of people that were like, wow, that's so cool. And then, damn it, that's not what I wanted to hear. So that's how the tether incident worked. And that's one of the many that I think that was NASA's unexplained files they did that for. So I worked on many of the episodes of NASA's unexplained files. So now I'm doing proof is out there on A&E. So those are the interesting types of cases you get all the time, right? So anyway, so that's that one. Now I saw some other questions. Daryl, if you want to talk about anything, go right ahead.
Well, you should probably address Pop Tom's question. I gave him a short answer. Does visible light travel at the same speed as infrared light?
Yes, it does. But light in general can change its speed depending on the medium it goes through. Obviously, light can't travel through rock, but it can travel through water. And the speed of light in a vacuum is how we always talk about that, 186,282 and change miles per second. Okay? So, in general, that's over 7 times around the Earth in 1 second. And that's the speed of light. And at that speed, that light moving that fast still has to travel 4 whole years to get to the nearest star. That's pretty far. So, the universe is vast.
And you can sort of expand the horizon some instead of saying light, whether it's infrared light or ultraviolet or visible light, radiation in particular. everything from one end of the spectrum to the other. It all travels at the speed of light.
Right, whether it's a gamma ray or a cosmic ray or radio waves. Radio waves are light. I know there's people out there listening now who said, really? You know, it's true. Radio waves are light. So, just a little point here. Notice this beautiful image, right? This is the North American Nebula. We have captured 3 images here. You see that? 3 right there. Okay? 3 of them have been captured, and we've ignored 19 of them. So when we come over to our full width half maximum, you can see that a couple came in, but the rest were ignored because I have it set to 8.05, and that's the only ones that came underneath. All right? So the longer we leave it here, the more images we'll capture that are good. But what this guarantees us is that we'll always get perfect images from now on. Because imagine if we didn't ignore these, well, then we'd have fuzzy, trailed images, and nobody wants that. Especially not an astronomer. So that's cool.
Papa Tom had a follow-up.
Okay, go for it.
Well, and again, I gave him a short answer. Would James Webb Telescope be able to see redshift? I said absolutely. Redshift is very much Webb's job.
It is, yeah.
And what you have to do to see way back in time, like Webb does, billions of light years away or billions of years ago, is that's where spectra come in, that we have known emission and absorption spectra of the different elements. And the farther the redshift, the farther those spectral lines are moved off their base position if the object wasn't moving away from us due to expansion of the universe or whatever. And Webb looks for those spectral signatures that are way shifted out of their normal static position. That's as you get so far off the visible spectrum that what is normally like the red hydrogen line, alpha hydrogen or hydrogen alpha or oxygen 3 or stuff like that, they get shifted so far that you're looking no longer in the visible spectrum at all. You're looking in the infrared to see how far away they are by determining how much the spectra had been shifted.
That's right. And that's the main feature of the Webb, is that it actually has the ability to see things that the Hubble cannot see and that our telescopes on the ground could never see.
Yep.
And that's because, as Daryl pointed out, all the data that was normally in the visible part of the spectrum, what happens is the farther away we get and the farther away we look, galaxies really, really far away are moving away from us at a faster rate. That was one of Hubble's tenets, and he came up with the Hubble constant. And that Hubble constant was the speed of a galaxies moving away from us the farther out we go. It was supposed to be a straightforward relation. It turns out that it's not. It turns out that the Hubble constant isn't a constant after all. So it had to be recalculated because it turns out that the universe is expanding and accelerating as it does so. So the expansion we expected, but the acceleration we did not expect. I'm going to answer a question about how many stars are within 100 light years. The answer is about 60,000 stars within 100 light years of us. But once you get out to 1,000 light years, it drops off because we're leaving the spiral arm at that point that we're in. And so you get less and less stars for a period of time. So anyway, going back to the redshift, that's like 2 questions in one. Sorry about that. So going back to the redshift, the Webb is able to see then these massively redshifted galaxies where all of the visible light they have has now been shifted way out into the red. See, my hands are gone. You can't see it with your eyes, and you can't see it with the telescopes on Earth. And even the Hubble, which has infrared capability, can't see that far into the infrared. The James Webb can see like 15 or 20 times further out into the infrared, maybe more. It's 100 times more powerful in general because of its 21-foot diameter mirror versus the Hubble's 8-foot diameter mirror. You know, so I think that's pretty cool.
Yeah, and Webb has looked at some of the same fields that Hubble did, and where Hubble ran out of juice, so to speak, because they were looking no longer in visible light. It may have limited infrared capability, but mostly visual. When they looked at the same area with Webb, they saw a whole lot more stuff that was shifted out of visible into the infrared.
That's right.
Again, that's why they built the Webb.
That's right. I mean, Hubble does have infrared capability. In fact, it's looked at the pillars of creation in the infrared. But it's only going into the infrared a certain distance. Infrared's huge. It's a huge bandwidth. And the Hubble could peek in, pretty far. Okay? But it couldn't get all the way to where it had to go. So obviously the James Webb was specifically made for that. Now, example, when you're going that far out, the infrared system has to be absolutely out of the sun, meaning the Webb, the Webb could not orbit Earth, because if it orbited the Earth, there'd be periods of time where the sunlight would fall on the instrument package, and they couldn't spend time keeping that back into the Webb with its guard there, its solar guard, facing away from the sun. We couldn't always have that happen, okay? So now it's only doing station keeping 1 million miles away. It's not in an orbit around the planet. It's sort of in an orbit around what's called a Lagrange point. I liken them to parking spots in space where all the gravitational forces kind of sum to some value close to zero. So you can put something there and it'll kind of stay there with a little help, a tiny bit of help. And that's the fuel that James Webb carries on board. They've already started talking about ways to refuel the James Webb Space Telescope after the 10 years is up, when its fuel will be exhausted, because it has to maintain like a figure-8 orbit out there, or like an elliptical orbit around this Lagrange point, actually. So to do that, it needs fuel to keep it just kind of on target. Otherwise, it'll drift out and end up just becoming, a satellite that doesn't have any control once it runs out of its fuel. Yeah,
and if, say, you looked at the Hubble Deep Field, one of the ultra deep field images, the faintest, smallest, reddest little blobs you can see in those Hubble pics, when you look at them with the Webb, guess what? They turn into galaxies.
That's right. And as Daryl was mentioning earlier, and as I said, the James Webb's approximately 100 times more capable than the Hubble Space Telescope. And I do talks around the country. One of the things I talk about is the difference between Hubble, James Webb, and things like the 20...
Chandra?
No. The ground-based telescopes, like the Geminis, the Kex. And I compare them, And so when we look at things like James Webb, it's a leapfrog of capability. It's actually so much of a leapfrog, we're almost not quite ready for it. We're almost not quite able to process everything that it has to offer. But that's something that is very obviously, that I'm up for the challenge. Everybody's up for the challenge, I'm sure. So I think it's pretty cool. If there's any other questions we haven't gotten to, I'd like to make sure we get to them.
One thing to consider with the Webb being out at the Lagrange point, to keep that solar shield between the telescope and the sun, that solar shield has already blanked out basically half the sky. And what Webb can look at any time, I believe, is going to be kind of a donut shape of sky on the other side, on the dark side of that shield.
That's right. And then,
And as the Earth goes around the sun in the course of a year, well, the Webb will also. And so that donut is going to change over time of what's visible at any time. You know, like we do here on Earth, what we're looking at in Cygnus right now, well, that's primarily a summertime object. And 6 months after this, we're going to be looking in the winter sky over toward Orion or Monoceros or one of those things. And that's, I guess, the constraint that the Webb has.
okay.
It's limited in what it can look at in the sky at any one time.
That's right. But again, we have time on our side when it comes to the Webb because, as Daryl pointed out, as we go around the sun, so too does the Webb. And its sky changes on a daily basis as well, by a few minutes a day.
Yeah.
I wanted to address Papa Tom. He said, is NASA thinking of a replacement of the James Webb after it runs out of fuel? Actually, I mentioned it a moment ago, Papa Tom. They're actually thinking of designing a refueling mission. And so the James Webb Space Telescope was designed with a potential to allow an automated refueling mission to go and refuel the fuel that is required for the Space Telescope to continue operation. So that's pretty cool. Oh, and Vince Giggler just said there are a couple of replacement projects for Webb. He's right. Absolutely right.
I wouldn't imagine if it had Starship written on it or SpaceX or something when they make it out there.
Oh, yeah.
I think, you know, it's like with the Hubble. Well, they just sent up a space shuttle with new components, and the astronauts would have trained on how to install those new components or fuel or whatever.
Yep.
When you're talking going a million miles away, well, if they're going to be manned spacecraft, you know, you're talking next generation kind of stuff that will be sending people out for missions a million miles away, or, you know, that's like going to Mars
Yeah.
or whatever, you know, everything. We're talking down the road.
Well, they
Then again, maybe they'll do it with robots.
that's the idea. I was going to say they're actually looking at robotic resupply missions already. Again, this was designed. In fact, I saw some prototypes. The refueling hardware on the James Webb was designed so that robots could grab it, take off connectors, and put on connectors to do resupply. And if you think about it, that's pretty impressive. So that was good foresight too, thinking as well. So I have a feeling that that they'll probably have a robotic resupply mission for this.
Yeah, robots are boring. Manned space, you know.
Not if
manned
they
space
have a
flight.
camera on them.
Oh,
If they
you
have
know
a-
what I'm getting at.
Yeah.
I mean, where's the romance? There's no romance in robots.
Right. I mean, just think you're like a slit.
Well, actually, the Japanese would disagree with that.
That's right. There's a
Oh,
slit.
that's a-
There's a
another
slit in
subject.
your suit that's you know you're one step away from an awful death if you get a slit in your suit out there. So I think I'm okay being on the ground, to be fair. Because
yeah. I'm sorry. Steve Tuttle has a question. Has the Webb telescope taken images of the black hole in our galaxy yet? Actually, yes, they have. I saw a picture just yesterday. It was really eerie looking, too. It was a black and white image, oddly enough. It may have been a raw image, but yeah, they did an image of the Sagittarius A star area, and it was really strange looking.
well, define strange looking.
Well, there were stars, but there were great big wisps of stuff too, big curly wisps out in space around the area of Sagittarius A star. Give me a second, I'll see if I can find the image.
Okay. put a link in. All right, so guys, we've been sitting here imaging the North American Nebula. Notice we were able to capture 6 frames and 48 were rejected. So we go to our log here, we can see how many of these images got rejected because their actual star diameters were too big because of wind. We have 11 to 23 mile per hour winds at the observatory right now, and we're actually imaging and capturing images and still getting perfect images because we're able to use this filter to knock out any bad frames automatically. It means it takes longer, but it's still pretty cool. So what we'll do here is we'll save at this point. This is the North American Nebula wall. And we'll say save exactly as seen. Yeah.
Okay, I'm going to post a link in chat. This is the picture from Reddit, so bear with me. It's black and white, and it's only part of the image I saw. But this is maybe to give you an idea of what I was talking about. And I found another color image, but I don't know the particulars of it yet. This is the one I just posted in chat's about half of what I saw a day or two ago.
Okay.
Yes, it says it's a raw image of Sagittarius A by JWST.
Okay. Let's see if we can actually show that. All right. Okay, so that image is right here. So this is the Sagittarius A location right there. And again, it's only part of the image, as Darrow pointed out.
I still see the Cygnus wall.
I know you do. That's because you're getting a screen
right.
share. You're not getting
the
whole.
Very good. I'm at
at
YouTube now. I see it.
Yeah. Hey, Gladys is here. Hi, Gladys. Genghis, what's up, brother? I said I answered your question, but didn't say hi. I'm sorry. Donald Kunzer's with us. How you doing? And Cosmic Ray, to answer your question, yeah, the Three Stooges made it. You called it the Stooges. You meant Stooges, I think. If it was 75 years ago, it's only 75 light years out. However, we have been giving off plenty of amazing radiation to be captured, right? And among that radiation to be captured is, for instance, all of the radiation from that comes out of our atmosphere that has gone out into space, and for around 2 billion years now. That's billion, not million, not anything, billion with a B. Okay, we've been generating oxygen in our atmosphere, and that oxygen signal has been sent out 2 billion light years. And if you're a carbon-based life form in the universe, you need oxygen to survive. I've said this a million times. Carbon is the 4th most abundant element in the universe. Oxygen, the 3rd most abundant. Then you have helium, and hydrogen is the most abundant. And between hydrogen, oxygen, and hydrogen, these elements make up life in general. Those are part of it. There's a lot more, obviously, but they're the essentials. And so if you're a carbon-based life form, you will require oxygen to make energy and to process energy. So therefore, you would, as a carbon-based life form, look for other carbon-based life forms when you decide you're going to start looking. And why is that? Because every life form on our planet has curiosity as a factor that drives them. Every single life form, from the smallest to the largest, they're curious. Okay? So I think that's probably a universal template of life in the universe. And so, therefore, there will be other groups out there that will say, hey, I wonder if there's more like us out there. And they'll start looking. And if they're 1,000 years ahead of us, their technology is going to be 1,000 years better, whatever that means. So they'll look for oxygen in an atmosphere and say, hey, why is there oxygen in that atmosphere? The reason is because life created it. All right? So they might see dimethyl sulfide in our atmosphere as well. That's the smell of the sea. Every time you go by the sea at low tide, it's like, phew, what's that stink? Well, that's the poop of many different sea creatures that you're smelling, okay? And it's the smell of the sea, it's the smell of life, okay? So if that's in our atmosphere, oxygen in the atmosphere, it means that there's life here. So they'll see it. And again, we've been sending that out for over 2 billion years, because that's when oxygen started building up. So that said, I have a feeling that life forms could have found this a lot easier, and from a long, long time ago. So, hi, Marianne Robb. Marianne is one of our 3 principals in the Skytour Livestream Observatory and in the SkytourLive.org organization. Right up here at the top, you can see it right here. Go to SkytourLive.org if you want to get interesting data and see all of our pictures for free like this. Then go to our Etsy store, Skytour Shop, if you want to buy a nice Christmas present. And I'd like to thank Izabela, who has produced a phenomenal Christmas video for us for our Skytour Shop. It's really, really quite nice. It's stunning. Anyway, that said, let's see if we can move on now, because we got 6 good frames, and the wind is quite heavy out there, so we only got the 6, so we're not getting any more. So we'll leave it at that. I already saved this, but I'll do it again just to be safe. Yeah, see, I already did. That's why it gave me that message right there. And I do this again, and it's going to say it again, and I can't. All right, good. All right. So now we'll go back and go into our rapid movement view here. You'll notice when we go into this, you'll see it gets brighter, and you'll see the stars will dance around a little bit because of the wind. And if they dance too much, we won't be able to actually won't be able to see them, and they won't be captured by our process. Okay, so let's go back and see what's else to look at here in the sky for right now. I did want to check out. I want to move across the sky here. Hey, old school, how you doing? Is old school talking about a number of stars near us?
I see that.
Is that what his question is?
Well, yeah, this goes back to that. How many
stars within 100 light years?
Within 100 light years. Old school.
The number's about 60K.
Yeah. It may depend on how you posed the question in the search engine. I said how many stars within 100 light years, and it said 60,000, which is very, very close to what Calibos said.
Yeah.
59 some odd thousand.
That's what I also said prior, I believe.
Yeah.
All right, we're going to move now. Here goes the telescope. See it move. Ray, when you say, when somebody sends out a message, are they going to wait 1 million years to hear back? No, they're not. Okay, that's not the point. The point is that if you are sufficiently advanced, then you can travel here and explore. And you might say, well, that's impossible. Space is so big. Well, not by my judgment and by the judgment of other astrophysicists and folks. I think that if you talk about Kaluza-Klein gravitons, then you might find yourself with a fifth dimensional travel possibility. This is a very popular lecture I've been given all over the country, and I've had physicists in the audience, I've had scientists of all kinds in the audience, and they agree it's a fascinating concept, but we don't have the proof yet for it. However, CERN is actually doing that right now. They've got the Atlas project running, which is another accelerator. Its purpose, the purpose of Atlas, is to explore in part Kaluza-Klein particles and look for the elusive Kaluza-Klein graviton. So we're talking about a possibility that we might actually see perhaps in the next 5 years, 10 years, some evidence that these interesting particles do exist. And if they do, then it means that those particles can be utilized to travel interdimensionally. And it lives within string theory. String theory has to be proven. But honestly, you'd have to see the talk to understand it better. It goes into the fundamental forces in physics, the strong force, the weak force, electromagnetic force, and then of course gravity. But it's all at a layman's level, so it's written for everybody. It's something everybody can understand. I had someone in Texas when I gave this talk. They were so taken by it that the guy gave me his cowboy hat. What do you do? He said, "No, thank you." I took it. It's a really nice hat, actually. He says this really puts it all together, and that's the thing that I was aiming for, was to help put it all together. So it's pretty cool. All right, let's move this over. We are at a place called the Heart Nebula, and we're going to be looking at the heart of the heart. I believe this is a good positioning because we got some stuff here I believe we want to look at, and there's some things here. I'll just do a quick shot and then see if we're going to move it or not. I'm just going by memory of what's here. Sean, hey man, thank you for that. That's very nice. Super chat donation. Hey, look at, we love the support of our SkyTour family. And if you're of a mind to, please join our Patreon. We need all the help we can get, for sure. Okay, there we go. We got some of that there. I'll just move down a little bit. That's what I thought. Okay, that's good. All right, here we go. So let's go to do this again. All right. So now we'll just head up north a little bit and move just a little bit westward.
I saw the fish head up top right, I think.
No, it actually wasn't. The fish head is much further up. You're like, okay. That's more the center of the nebula. I'm trying to get the center. I was trying to get there's an eastern side that's actually pretty interesting. But we'll get it. Okay. So we'll move west a little bit now. See, the fish head will be way, way up to the upper right here. And you might see an edge of it. But so this is this right here would be a good spot. So we'll just let this hold right here. It's now searching for a guide star. Once it finds a guide star, there it goes. It starts guiding. All right. And now we're going to say do a 25-second shot, which is 25,000 milliseconds. That's why I put that over there. All right. And then off we go. Okay. And so then we'll do our live stack. And that's the previous shot we took. That's up on the up at skytourlive.org on our server right now if you want to see it. All right, and you can download it for free. Just wanted to show you guys, okay, for those that may not remember, okay, this is our telescope control section here in the red box. This is our telescope computer right here. Here's the image of the telescopes in the buildings. That's right there. This is our stacking screen where we stack all of our images. Okay, and this is the camera control cluster over here, culminating with this here being the focus, and this here being the exposure. The most important fields in this whole side are this one here, the exposure, okay, and this one here, the gain. Okay, so the exposure is how long the sensor is exposed to light, and the gain is how sensitive that sensor is set. The more sensitive, the more noisy it is, the more grainy, but the more detail you can see. So it's a trade-off. You know, do you do a lot of that or do you a little of that? So we'll wipe that away. Okay. And obviously our full width half maximum values have not been met. But what I can do, just to give you an idea, is I will shut it off for this next exposure. Just to kind of show you what's coming in. Calibos, thank you. That's Mike and Tiffany. Michael works for SpaceX. He's a really, really cool guy. Yeah, here we go. And there is the Heart Nebula here. That's the rough center.
Yeah, okay, that's the bright spot I saw before, which I assumed was the fish head.
Yeah, the fish head is just out of view up at the top here.
Yes.
You can start to see a little brightness. It's so big that we would actually have to do a multiple shots. Oh, look, we actually got a good one. How about that? Well, I'll turn the full, I'll put on the full width half maximum on again. No, we didn't get a good one. We got... With the wind blowing on the telescope, it's hard to get a good stack, guys. But, you know, if we wait long enough, we'll certainly get them. Oh, Ray asked how many out there do astro image processing. A lot of people do astro image processing. Izabela here in our chat does. I, of course, do. I wrote an image processing program that was used by the Hubble Space Telescope team. Gosh, years ago, when the Hubble first started getting imagery after it was fixed. You know, after it's got the glasses. The Space Telescope Institute was using software that my friend John and I wrote to actually process some of their raw images they were getting. And we thought it was a real kick to know that they were trying it out. But, you know, that's a business I didn't want to be in for long. I can promise you that. It was really, really very demanding. Hey, Rocket City Astro, I forgot to say hi. How you doing, man? Marianne reminded me by saying, "Hey, Rocket." I was like, "Oh, that's right. I saw the name." As you can see, we are getting some pretty strong winds out there. You can see the wind has been kind of hovering at probably 18 miles an hour. As the desert cools off at night, you get these winds along the surface, and the winds will tend to go away probably around 10 o'clock Arizona time, which is midnight our time. All right, and we kind of, you know, we kind of we kind of could wait that long, but I don't want to make you wait. I thought it'd be kind of cool to do this, so we see a few objects and get going. Michael Hedrick says to Marianne, he's talking about food. Food? How could you be talking about food at a time like this? Hey, Robert, how you doing? Robert Thallium says, hello from Snobsdale, Arizona. Oh, I spent a lot of time in Arizona. I know exactly what he's talking about. Very cool. Well, wait a minute. You're not a snob, though, if you're here. Right? I would think that's true, Robert Thallium. Thallium's an interesting name. I do a lot of model work for the Navy, and one of the submarine models has these thallium lights that it uses to see on the bottom when it's down so deeper than you would imagine submarines can go. So I like the name Thallium. Yeah. Cosmic Ray says, raw image to finished image is more of a task than collecting image. Oh yes, absolutely. I've written little subroutines for Photoshop that actually do a lot of the work for me. I shared them with Izabela. She uses them. Actually, she's the only one that has they're called action sets. She's the only one that has my action set for Photoshop. And it allows us to process and remove, things that don't belong. It allows us to enhance faint things, a particular kind, like dark nebula. Like this is a dark nebula in here. You want to enhance this. Well, the first thing you have to do is get rid of the stars. So we actually remove the stars, and I have a commercial product for that. And now you have just the nebula, and now we can do all these actions that I wrote on the nebula. And then you can draw out the details of a dark nebula versus a bright nebula, change the colors to be more appropriate, balance the colors. And then you can we also take mosaics where we take images that are overlapping images of objects, and then we stitch them together. And when we stitch them together, we process them all at once. Izabela's not responding. Yeah, I said little action figures, right? A little tiny Izabela. I got it. And then here I come. Okay, I got this one too. Can you imagine if that's what it was? Little robotic me and Izabela's running around processing. Heave ho, heave ho. Wow, after all that, we only got 2 images, so the heart's not working out too well for us tonight. But what we can try is to image the Soul Nebula, which is down below it. And we'll try that. Or near it, anyway. It may be more of the same, but we'll give it a try. It was really windy tonight, guys, and so it really isn't the best night to do this kind of thing. But you guys have been waiting so long and so nicely. I had to do something. We can also image the double cluster so you can get a nice shot of that. Maybe we should do that first. Let's try that first.
Mark, would you excuse me a moment, please?
Sure thing.
Right back.
Yeah. Well, there you see the double cluster. The double cluster never fails to disappoint. And what we can do is we can use a short exposure here. And on top of that, I'll refocus because I want to get a perfect focus. Here's what happens, just so you know, it's kind of a strange effect, but when a telescope is moving, all right, when it's aimed horizontally like this, okay, if you look at me down here in the corner, when it's aimed horizontally, the mirror is one way, okay, but when you aim up, you get something called mirror flop, the most imperceptible shift in the mirror backwards. It's linear. It doesn't go like this way or that way, but it just goes back a little bit. And mirror flop is a problem because it's well known actually, and my telescope here in the desert has it. All telescopes have it to some extent. There's others that don't. If you don't mind paying an arm and a leg, I could never do this for you if I had to pay an arm and a leg for a telescope, because then I would never be able to afford a building to stick it in, and all the remote gear I had to put together over a year of time to get this to work. All right, so here we are. So I'm gonna show you one thing here while I. If you look at the star images there, they don't really look like too much of a difference in color, but look what happens when you defocus. When you take them out of focus a little bit. All right, now you can clearly see the orange stars standing out. Okay, look at all the little orange stars everywhere. Okay, this is because the human eye and the sensor of the telescope, sensor of the camera, kind of work the same. If something's really, really bright, you can't see its color. But when you spread out the light, you can see the color quite well. I'm going to pop in one more level and then start the focusing process. And you can see how that works for those that haven't seen it. All right, so we're out of focus just a little bit, and we want to move into focus. So what we're going to do is start this process. We've got 7 stars. You can see it right here. 7 stars. It'll go between 7 and 8. And then we're going to start moving in. And we're going to bring the focus in and back out again. And that's going to make a focus curve that looks like a parabola. Okay, like this. And at the center of that parabola, at the lowest spot, that represents the point where the stars are the smallest during this focusing run. And that's the point we're aiming for, and that's the point that will become our best focus location. And then we tell it to go to the best focus, and our telescope will autofocus for us. So you can see that looks pretty good. That's probably the low end, and we're up to 202 stars that we're using. Now the number goes to 219, okay, 223, 228, all right. And you can see the settings here. And this value here is the same as the FWHM, full width half maximum setting as well. See, now it's at 6. And the best was 5.3. So now we go down. We don't have 100 or 200 and whatever, 228 stars. Now it's down to 126. And as you notice, we get to the other end of our little curve here, and the bottommost spot, that's our focus point. And we're waiting for 3 more samples. We're at 9 out of 12. But that's sort of overkill at this point. We don't need that. So I can just click and say best focus. And what's going to happen is, it's going to go from where it is now to all the way back here, and then slide back to the center. And as you can see, when we get rid of this, now our stars look gorgeous. Now they're beautiful stars. So let's now do a image here. We'll do, let's say, a 12-second shot, and we'll stack it. And then we'll save it for you guys so you can have it and download it, put it on your wallpaper backgrounds. And if you want any of these things on mugs, shirts, lamps, anything you want, well then visit the Sky Tour shop up there on the right. It's on, look at that. Wow. Let me just bring that in here. Okay. Alright, let me get rid of this guy. This is overkill brightness. Drop it down to normal brightness. Waiting for Starlink to re-engage. There we go. And now you see it. Look at that. Nice. Welcome back, Daryl.
Thank you.
Okay. So there's the double cluster. We have 2 stacked. That's really cool. We have 4 stacked now. And we'll darken up our background even more. Look at how beautiful that is. And these 2 clusters, what's interesting is, I believe this cluster is the one that's actually closer to us.
Yeah.
And that one on the right is a little farther away. So you can see that its angular size overall, on average, is a little smaller than this one, which looks a little bit more spread out. That's just because it's a little closer to us. And these red stars are red giant stars in that cluster.
Yeah. Cluster stars tend to be the same age because they all formed at the same time. That there are red giants in the cluster shows how old they're getting, that some have already moved off the main sequence.
Yep. The main sequence is the spot in their life when they fuse hydrogen into helium, like our sun. Our sun is a main sequence star. All stars, when they start out life, in general, are main sequence stars, fusing hydrogen, the most plentiful fuel in the universe, into helium, at least initially. Then they can go helium into carbon, through some isotopes of nitrogen, and then into oxygen, and all the way out to iron, number 26. But it can't go any further than that, because every reaction before that in the fusion sequence, and Daryl knows this too, every reaction before that gives off energy when fusion is done. But iron requires energy to fuse anything farther than that. So the star cannot go past iron. But you'll say, wait, there's 118 elements in the periodic table. Where do they all come from? Some of them come from colliding black holes. Some of them come from merging neutron stars. Some of them come from supernovae. Some of them come from stars like the sun that are generating them through a process known as the S process, or the slow process. It's called neutron capture. What's interesting is when you look at an atom, right? A hydrogen atom has how many protons? You know, go ahead. I'm listening to everybody out there in chat. Yes, someone said 1. That's right. 1 proton in the nucleus and 1 electron cloud around that proton. Well, if you actually can get a neutron to go into that, you'll have a different isotope, a flavor of that same atom. And that flavor, when you have an additional neutron, is called deuterium. And deuterium, then, that neutron, under certain circumstances, through this process, can be converted into a proton. All right? There's a whole drawn-out thing there. But that said, that process is what we're talking about. All right? When you have a neutron converted into a proton, now you have 2 protons in a nucleus, and that element is not hydrogen, it's helium. And the same thing can happen in a variety of ways down the line in the periodic table. And stars like the sun can do this. More massive stars from the sun can do this. And then they can go supernova later as well. And make even more elements. So it's really, the stars are element factories. Okay, we're going to go to 20 exposures on this, and then there we are. Look at that. That's really pretty. I'm going to rename this too. You guys will enjoy this one. This is called the double cluster.
Michael Hedrick has a question for you.
Yeah, I did see all caps. Thank you for that, guys. All right. Are you able to see what he asked right now? Because I'm just going to do this part right here. So
When a nuclear reactor starts up, it releases a huge amount of energy and bright white light. Do stars do the same when they start up? All I said was it's blue light and it's Cherenkov radiation.
That's usually when a reactor melts down that you'll see that. I saw Cherenkov radiation on an active reactor as I walked over it. It was a baby reactor at a university, and I walked over the gangway, over the thing, and they said it was totally safe. It was encased in water. And I looked down there, and it was bathed in a blue glow. And at first I thought, oh, what do they got? Blue lights? What are they trying to do here? And it says, no, that's Cherenkov radiation. Oh, wow. Let me out of here.
Well, that's when it's exceeding the speed of light in that medium, correct?
Not sure if it's exceeding the speed of light or... Um,
I think it is. Let me check.
all right. Okay, I just saved this, by the way, so this is now out there. I'll save it again. And now we'll have this. Now you guys can look at this. Let's zoom in so you can see what you're getting. It's like kicking the tires, right? You want to see what you're going to get.
Yes, Cherenkov radiation happens when electrically charged particles such as protons or electrons travel faster than light in a clear medium like water. When this happens, the water molecules and particles interact to give off light.
I don't understand the faster than light part, though. Because...
in the medium.
Oh, okay, hold on.
I mean,
okay, so when...
186,282 miles a second or whatever.
Right.
That's in a vacuum.
That's right, it is. So if water, if it goes that fast in water, for some reason, then this is when this happens. If it doesn't,
Yes.
normally it would go slower. So that could explain it. All right.
Yes.
I had a brain seize right there. Okay. Look at it. What do you think, guys? Now, you might say, oh, there must be a lot of life out there in those pairs of clusters. And the answer is that probably not at this point. These clusters are only, oh gosh, I forget how far away they are. But these are older stars, but I'm not sure about the evolution. They might be more massive. And so there's a lot of ultraviolet light because clusters tend to be young. But if they're hot young stars or hot stars and massive stars, then they'll run through their lifetime faster. So you might see red supergiants in a young cluster and say, how can that be? Well, it can if all the stars are massive. Like Betelgeuse, for instance, is only a few million years old. All right? It was a hot blue star. Just over 4 million years ago, Betelgeuse was a hot blue star. Now, it ran out of its hydrogen very, very quickly, and it expanded into a supergiant. That's part of the phase of stellar evolution it's in. And eventually, it's going to go supernova. Okay, so there we go. Now let's go to the Sol Nebula. Let's go back here, though, to FWHM. I want to see... Yeah, see, we got all of ours here, so we might be past the wind. Let's go see if that's true. So, this is up on the server now as double cluster. You can see that listed right there. And that's the name it'll have on the server when you go to skytourlive.org. Go down to the dark gray section just below the top and say, take me to cool pictures. And then you read the instructions there on how to navigate into the directories to get your pictures. All right, so that's cool. Nice. So, let's get out of there. Let's come back here. You still there, Daryl?
Yes.
Oh, okay. Sorry. I thought I lost you. I thought I lost you.
Don't have anything to say.
No, that's all right. I'm never short of things to say, apparently. Okay, let's go down to the Sol Nebula. And you'll see the telescope now is going to head just a little bit south. There we are.
Thank you, Izabela. I forgot to post that tonight. I'm a bit rusty.
Thanks, Izabela. Okay, so let's go and see this cluster of stars here. Let's zoom in. Okay. Let's actually align us with the Sol Nebula. All right, so there is that cluster. And we're going to see the Sol Nebula. This red box represents the size of our field. All right, and the size of the field, you'll notice it's upside down. All right, it's 1.1 degree, 29 minutes by 1 degree in height. So we're going to see that we're going to image this part of it if we can center up the cluster. So the cluster is right here.
I think I see a star baby.
I think you do. But maybe not with this particular camera. With the other camera, yes, we caught the entire Sol
Right.
Nebula.
Right.
This time we're going to capture a segment of it because we're zooming in and we're going to actually capture a section with more resolution than before. So this is pretty interesting. Here we go. Okay, that should be good right there. So don't do that. I didn't want you to do that. Come back. Okay.
Broncos scored a touchdown with a minute to go. They took the lead. Sorry.
It's okay. I don't follow sports. I'm kind of boring. All right. Let's do this now. Let's say 25 seconds. So you see beautiful stars, and in just 25 seconds, we're going to see the birthplaces of stars. So we'll cut this down here, go into our live stack here. And we're angled kind of low, so we might get away with, oh, that's just beautiful. So we'll clear this now. 5 seconds, 4, 3, 2, 1, and our first image. There it is, coming in. All right, so let's back out a little bit. Okay, if I can get my control back here, please. All right, so I will do this. We will normalize our curves. All right, now let's just zoom out a little bit. There we go. So now you can see a little bit more of what's going on here. Look at that gigantic, beautiful nebula. You can already see dark nebula over here. This is dark dust. Again, when we talked about the way elements are created in a star, when it goes supernova, that stuff is dispersed to the interstellar medium. When stars reach supergiants, like you saw in the double cluster with those red stars, they will many times form, because they're so big and distended, the temperatures are lower, way far out from the middle of the star, the center of the star. And so molecules of carbon can form out there. And those molecules are, of course, black or dark brown. Silicon atoms can form out there, or can form molecules out there. And you basically get interstellar dust grains out there. And that dust is what we see littering the universe. It's everywhere. There's some here, there's some here. There's some interspersed throughout all of this. It's really quite something. Let's try and pull that out. Okay. So there you can see this dark dust is starting to get really clear here. Yeah. Actually, you can see your star baby, Daryl, just a little bit.
I think I see its belly.
This is the belly right here. This is the arm.
Yeah.
And here's the face with the mouth.
Oh, okay. Yeah.
And there's the feet. It's a little embryo. It's like the Star Child from 2001: A Space Odyssey, all coiled up, coming back to rule Earth for 1,000 years. Cool. This is neat. Here, let's do this. Let's get this out of the way, and let's move the telescope out of the way and enlarge our view so we can see just this beautiful sky. There we are. Look at that. That is our amazing Soul Nebula.
Star Baby.
The Star Baby Nebula. That's true. He's right. It's the Star Baby Nebula. It's the Star Baby, baby.
Yeah, that's his little butt down at the bottom right, and his leg and his foot sticking up there. In the mid right, far right, his belly and his little hand at the upper left, and his maybe half of his face.
Yeah, little nose, little mouth. He looks like he's grimacing. There's the little butt you're talking about. There's the legs. Yeah, I think that's kind of cool. Star Baby, baby. Yeah. And Star Baby. It's actually the Soul Nebula, otherwise known as the Star Baby. Well, to Daryl, it's known as the Star Baby. He's the only one that calls it that. That's not an official name for it. It's known as the Soul Nebula. But it's alright. It's all fun, isn't it? Very neat. So we'll turn that off for now and develop more Star Baby. I'll come in here momentarily just to see if I can tease out some more detail. The way it works is these are the curves. These are the curves of data that we're getting. Okay. This yellow curve represents our what we're picking. Everything under this curve is what we're picking. So if we move out here, okay, then you see how the curve moves. We're getting some more of this space here, which is to the left of the dark curve. This is the curve that represents all of our data. The farther left we go, the more moonlight we're including, which is out here in this dark region. So it tends to be blue. All right. So as we move in, you'll see that we end up cutting out a lot of that extraneous light. And if we go right to the top, it'll be as dark as we can get it, and that's really pretty. See, there it is, Star Baby. Cool. Michael Hedrick says he sees it. Now, if we want to make this a mosaic, what we would do is we would move this cluster all the way over to here. Okay, all the way over to here. And then we would take a similar number of exposures up here at the front. And then we could get a mosaic. So maybe we should do that. Maybe we should do that. Let's see how many we got. We've got 14 stacks so far. We'll go to 15. Because it looks like we're getting what we need here, which is nice. Okay, so let's pull our stack back in. Again, if you have any questions, feel free. Stick them out in the chat there.
Calabos asks if you can home in on Jupiter. Maybe after, if you do a
maybe
mosaic here.
Yeah, we can see, because again, with a 1.5 degree by 1 degree field, Jupiter is still a little bit small. Our next telescope will be specifically tuned to looking at planets and other things up close. So, for instance, when we look at the Soul Nebula next time, our field of view might just be this right here. And that's it. I mean, it's going to be a pretty tight field. So I think that's pretty cool. But, all right, so we got 16 here. Let me just rename it. This is the Soul Nebula. Or Daryl's Star Baby. What's funny is Daryl told me when he first thought of Star Baby, I immediately said, "Oh, a Star Child from 2001: A Space Odyssey is what it looked like."
Well, sure.
And I thought that's what he was talking about, but he wasn't. Let me bring our telescope back here. Let's move this over and get that back in.
I guess it could be.
Why not, right? It's an artistic impression.
Oh, it doesn't look like Kiera delay.
No. Okay. All right, there's 18, so we're going to save it now. And then save exactly as seen. Okay. So what's up there on the server? This, what I'll show you right now, here is the image that we'll see on the server. All right, when it comes in. So that's what's up on the server right now. And you can download that and enjoy it all you like. And it's all free. Doesn't cost you a penny. If you join us and support us, well then you get far more highly processed images. And so you'll see details you just can't see. No noise, no grain, nothing. It's all very, very beautiful imagery. Okay. All right, so this is good. We saved it. So now I'm gonna get out of here. And take us to that next spot, which is just to the left of all this. All right. All right, so we're going to go now to the left, so we're going to basically move east. East we go. Okay, this should be good. And then we can make this into a mosaic. Hello, Marco. How you doing? Okay. Now we'll change this setting here. If it ever comes back. Okay. So 25 seconds. Waiting. Jeez. I wrote that a long time ago. Alright. And now we start. And we can go into our live stack. You'll see the old image first, and we'll delete that. Unless I did already. Okay, good. There it is. That's the old one. And that's also gonna have plenty of what's called dynamic range to allow us to modify and check things out. So we'll clear this now. And now if this first one comes in like it should, we'll see. Let's see if we got our... Yeah, we did. Look at that. And there's the other part of this head. There's the head right there. There's the eye and that little mouth with this very, very ornery little kid. You notice how grainy it looks, right, when you see it? And that's the noise of the sensor. And we actually have it super cooled. It's down to minus 20.5 Celsius on the sensor. So it's actually pretty chilly.
How did you manage that?
Huh?
How did you manage that? It didn't seem like you could ever get it down that far before.
Well, the temperature out in the dome in the building is actually 13 Celsius now, not 25 Celsius.
Okay.
So the deltas allow us to get down.
I understand.
Deltas are the changes in temperature that we go in. If we're at 25 Celsius, we may not get below negative 5 on our thermoelectric cooler on the camera. But if the temperature is down to freezing, we could get down to, 50 below. But this camera really is best used at like 20 below or so. It could go to 30, I think, but I don't think I would, C&D boy, well, thank you. He says, Maria, Marc is being wonderful tonight. No need for the taser, but might as well keep it on charge. Oh, thanks a lot, C&D boy. Jeez. All right, after we do this, we'll look at Jupiter, though, for Calibos. I saw cloud bands the other night, so it was actually pretty good. Notice here by the head, let's get some processing done here. Let's go right up to the black curve, get it almost as dark as we can. Okay. So now you can start to see how this detail's coming out here. This detail, although it was present with the other camera, it's actually far better here with this new camera. So it was kind of hard. Now, the Soul Nebula is, of course, a stellar nursery. And the stellar nurseries are responsible for, obviously, creating stars. And they do that by having large collections of gas and dust, and stars form little mutual gravitationally contracting elements in each parts of the cloud, and those contracting elements contract because there's nothing around them to stop them. So stuff mutually gravitates, and once it starts, more stuff just piles on, and as it piles on, it gets hotter and hotter and hotter inside because it's pressing down. It's like when you press on something really, really hard, you feel heat, and that's because of the friction generated by the molecules in your fingertips moving so much faster. Well, similar but different methodology, you've got the atoms and the nuclei of atoms being pressed on so heavily from the exterior of this large cloud that they heat up. They're moving around and being restricted in their motion, but the energy has to go somewhere, so it goes into heat. And the hotter it gets, the warmer that cloud becomes. And there's a magic point, 13 million Kelvin, where hydrogen fusion will begin. And so all those hydrogen atoms, because that's predominantly what's in these clouds, gets compressed and compressed and compressed. And as it gets compressed, we end up having this situation where the hydrogen now can wink on and fusion can begin. Now, before that happens, we might see some really interesting tendrils and north-south jets of amazing emission coming from this protostar, the pre-star situation. And those protostars are things that we've looked at before. We've talked about them on SkyTour Radio. And such protostars are also known as Herbig-Haro objects, and or HH objects. Now, Herbig-Haro objects are these young stars that are stars before they're stars, and once they wink on and they start doing fusion, then they become full-blown stars. And so, although they give off these jets of high energy that you can see sometimes visually and sometimes not visual, you will also capture a lot of light coming off when the star winks on. So yes, the star will start glowing bright color. Now, depending on how much mass is in the cloud when the star collapses, that star could be hot and blue, that star could be white, that star could be yellow, that star could be red. And most of the stars in the universe are the red kind, for the record. In fact, there's more M-type stars, which are the cool red ones, than any other type of star in the universe. And thus more planets around M stars than any other kind of star in the universe.
There's an astronomer on YouTube called Astro Biscuit. He's from the UK, I believe. He did a recent video where he borrowed a C-14 telescope.
Yep.
And took a close-up look at the Orion Nebula. Mm-hmm. His stated purpose was to find solar systems in the nebula, and
rogue
he
planets?
picked out not the rogue planets, but I think basically what he was looking at was like Herbig-Haro objects.
Okay.
Was what they wound up at. He found a couple visible at visible wavelengths, and then he looked at them with infrared, and one of them showed the star inside very clearly. He said he called it a solar system, planetary system.
Okay.
He may have been assuming a little bit there, but it was an interesting video, and he was getting a heck of a view off that C-14.
Interesting. I have access to a C-14. I actually was trying to. I was actually trying to. There was an auction, and was it you that told me about the auction, Daryl, or was it somebody else?
Yes, I told you about it.
And there was a C-14, no, a Meade 16, I think it was. Right? And the 16-inch Meade, massive hunk of steel and aluminum. And the weight of that thing is massive. And so as a 16-inch telescope, it would have been wonderful to have it in our observatory. The only problem with it is Meade is no longer in business the way they were. You can't get parts for it. So the telescope, it's normally like $18,000 or something like that. It went in the auction for like under $5,000. And sure, we could have bought it potentially, maybe, who knows. But the bottom line is, if it went sour, you're stuck. So I passed on it. I said, no, I got to have something that's reliable. So I don't know.
I gave up on Meade 20 years ago.
Okay, we're at 20 here in terms of exposure, so we're going to finish out on that. And do that. All right, so now we have a mosaicable Soul Nebula here. So if you want to do the mosaic yourselves, you can. If you don't, then we'll do it for you. In fact, I'm sure Izabela is already getting it downloaded, because that's how Izabela is. She'll get to it before me. She ruins all my fun. Not really. She makes it fun. Calvos, I want to thank you as well for telling people to give us thumbs up. That's really kind of you. I forget to tell people Do the like thing, do the thumbs up thing. We absolutely need all that. There's really no one doing what we do out there. There are people showcasing astronomy. There are people doing live streams of astronomy. But there's no one going to objects and saying, this is what this object is, this is this, and teaching you effectively an astronomy class. But it's okay, you know. It's something that I enjoy. All right, let's see here. Go down here, and now we're gonna make our way higher in the sky, because I think to answer the question of our friend Calibos, I think he wants to see Jupiter. So we're going to move the telescope, watch the telescope point up there now. It's going to be pointing pretty, not quite straight up, but pretty close.
It's amazing to see how fast Jupiter seems to be moving in the sky. It's actually the sky moving and Jupiter moving along with it.
Yeah.
I mean, Jupiter was in opposition back on November 2nd or 3rd, I believe.
Mm-hmm.
And I go out usually after sunset each night when it's clear, take my first look at the sky every night. And Jupiter is already high up, pretty high up in the east, and it's not even dark yet.
Mm-hmm.
So, and that motion actually, a little bit could be Jupiter moving in retrograde during, after the opposition. You know, it moves, changes direction, it moves east to west across the sky for a while.
Yeah.
But mostly that motion is actually Earth passing Jupiter.
Catching up to it, yeah, in the orbit.
We caught up to it on the 2nd, and we're moving ahead of it now.
Yeah, let's...
So we're seeing it rise earlier and earlier every night. There you go.
Okay, so there is Jupiter, a little wind, as you can see. So what we're going to do now is... don't worry, we're going to get better views here in just a moment. I'm going to zoom in on this, because I'd like to actually show you which moons are which. Okay, so we have Ganymede and Callisto, okay, and we have, trying to see what that is. It looks like it's got to be Io or something. Yeah. Okay, so Io is just emerging or going behind the disk of Jupiter. So if we were to reduce our exposure here, actually reduce the reduce this gain down to 0. Let's see if that does it. We might still have to reduce the exposure here. The wind is causing those oblong-y motions you see there. Okay, so if we can drop this down to half a second, okay, you'll see how much of a change that makes. I can't really tell. I mean, it's kind of hard to see whether this is Jupiter's occulting this yet or cutting it off.
I think it's passing behind.
That's what I mean. So I'm trying to see if Jupiter's cut it off already.
Yes.
Because in Stellarium it doesn't show it as being behind it yet. See, look at.
Oh, let me check one of my sources. Europa to the left.
Yep. Ganymede and Callisto, and then
to the right.
Io
and,
right there somewhere.
Yeah, I'm looking on JavaScript Jupiter, and it shows Io gone already.
Okay, so it could
Also shows the great red spot on the right limb of Jupiter.
Oh, let's go see if we can capture that figure while we're here, check it out. So,
Somebody messaged me, and I don't see who it was.
Izabela says the mosaic of the Soul Nebula couldn't be more perfect. I love it. All right, so let's bring down our.
Oh, there it is. Yes, well done, Izabela.
Oh, look at that! There's a red spot right there. You see the red spot? Can you see? There's the cloud bands there. You have the white zones. You have the dark bands. And the red spot is right there. With moments of good seeing, we can actually see it.
Yep.
That's pretty cool. Now you might say, well, can you get a picture of that? Well, unfortunately, we can't guide on something like this to capture a picture. We can only do like a video and then do a long-term stack of that. And that's something that I've done before, like with PIP, pretty good planetary processor. There's other products now. You can actually see the red spot right there, guys. It's really, really faint, but it's there. Let me just back out a little bit to help. Yeah, look at that. Not bad. Again, for a telescope designed for wide field, that's not a bad catch. Hey, Fantasy, what's up? So once again, if we brighten our time here, right? Let's go a little more. Oh yeah, the red spot really shows up here when you do that. All right, now let's. Jupiter has to be very overexposed to capture the planets. Wow. Okay. So here are the moons around Jupiter. This is Europa. You're looking at a moon that's over 5 astronomical units away from you. And it's actually it's as a 5 astronomical unit away moon, it's 2,000 miles across. So we're seeing that it's somewhat bloated. It's a lot smaller than this in real life. But because the light falling on the sensor kind of makes the image get a little larger. So we're seeing this bloat. Right? Then over here, we have the largest moon in our solar system. It's called Ganymede. And it does look bigger than Callisto here.
Yeah, it's actually bigger than the planet Mercury.
That's right, yeah. So it's,
Mark that.
I saw it, yeah. I was about to try and figure out how to get this up there. Let's see if we can... I'll save it to downloads. There we go. Excellent. All right, so now what I'll do is I will... Let's go back to looking at Jupiter and its bands. Let's get down to that. Okay, it's not quite good like this.
What were you calling bloated, Jupiter?
No, I was saying the moons are bloated in size.
Oh, okay.
Jupiter's not. Jupiter is more. It's more diffuse light across many arc seconds versus.
Yeah, I thought maybe you were talking about it being oval in shape, ovoid.
Oh no.
Well, it is.
Yeah, no, I wasn't talking about that though.
Okay.
Yeah. But it is, and of course, because of its rotation rate, it rotates very fast for a 80,000 mile diameter planet or so.
9 hours and 56 minutes.
Yeah. All right, let's. All right, let's keep looking at that for a minute, and while we're looking at that, I will bring us up something else. And yes, I know you can't. Your view will be affected, but you're the only one, Daryl. So, all right, hold on. Let me. Well, Jupiter does look bad. Not bad considering.
As you said, I mean, that's going to be one for the C11.
Oh yeah. Yes, it will.
And if you run a video of it and stack the best images off that, that's where you build up the really pretty detailed images.
Yep, that's what I was mentioning before. PIP. Pretty good planetary processor. PIPP. Planetary image. Pretty processor. I don't know what it stands for exactly. Let's go to see if this works. So yeah, this will work. So I want to see. We had taken a picture before, guys, of the Soul Nebula and made a mosaic. And actually, Izabela made the mosaic, as I figured she would. And here it is. There it is. That's Izabela's mosaic that she made. And it's really pretty. And you can see there's the face of the baby, the mouth, the arms, the back of the head, the shoulders, the baby's butt. Alright. This is the Soul Nebula, though, and it's Daryl's star baby. But look at it. It looks like a right foot and a left foot. I mean, it really is pretty cool. You know? Kind of cool. And you can see the details already appearing in this area here, which will be even more clear once we process this. So,
thank you, Izabela.
Yeah, thank you very much, Izabela. That was really pretty. All right. Very nice. Cool. Well,
There's quite a little dark cloud in his hand there.
I know, huh? That's cool. So there's Jupiter by request. And one of the things I wanted to mention too was because we use Starlink for our internet, out in the desert, we're actually at what's called a low bandwidth location for Starlink. It's not high bandwidth yet. Calabos can shed some light on that working at Starlink, or it's at SpaceX. So he might be able to tell us if we can expect to get better bandwidth out there. I haven't asked the question yet. I was just happy to get it at all. We were using HughesNet before, and that is more like BlowsNet. Doesn't even work. 3 megabits per second upload speed with 25 megabits per second download max. And the 3 often went down to 1 megabit per second upload. That is not very, very big. And we couldn't stream very well with that. We'd have frozen screens for like 10 minutes at a time. Totally unusable. Cosmic Ray talks about the metallic hydrogen core is envisioned for Jupiter. I mean, we say the words metallic hydrogen. Well, hydrogen isn't metallic, so what are we talking about? We're talking about a superfluid that is condensed so much that it becomes conductive. And so that explains why Jupiter can generate with its core such high magnetic fields, because it's creating massive electric fields in its core. And those electric fields naturally will generate a magnetic field as a counterpart. So Jupiter's magnetic field is, 20 times bigger than the Earth's. And thus its radiation belts are a lot bigger as well. Now, what are the radiation belts? The radiation belts are the magnetic field that stretches out from the planet, which is fine. The magnetic field would help us, protect us from ultraviolet radiation and stuff like that. However, those magnetic fields also trap charged particles from the sun, the solar wind, so they become highly irradiated magnetic fields, and those become the radiation belts. We have one
Those
called the Van Allen radiation belts.
okay. Took the words out of my mouth.
Oh, sorry.
No worries. And that's why we can't go to Jupiter.
Well, not
There
yet.
are. Huh? I'm sorry. What'd you say?
I said not yet.
Well, there are some fairly well-known pictures of like tourist spots. Let's go ski on Europa, stuff like that, and visiting the moons of Jupiter. They're done up like travel tourist posters.
Yeah.
And what they don't tell you is radiation would probably kill you in short order.
Yes. Quite frankly, it would. Okay. Okay, we're going to do one more object, and what I'd like to do is the Triangulum Galaxy. So, we're going to head here now. So you watch the telescope and point back that way a little more, out the back end. But it's actually pretty high in the sky, so this should actually be really pretty. And we'll just get this set up to show you. And again, what we're going to do is okay, look at the wind out there. Holy cow, look at that. We got a lot of wind out there. I'm not too excited about that. Let me just check something real fast. Okay, well, there's no precipitation. We just have wind. So not too exciting. Well, anyway, we can still check things out here. All right. Let me put the gain back up to where it was. Now increase. Wait, look at that. We're up at 200%. I meant to be at 25, so there we go. It's taking some time for us to for the system to react to us. Here we go. And right there is our target. Alright, so we're going to go east a little bit. Okay. Yeah, we're pointing straight up and being buffeted by wind, you know. In reality, I probably shouldn't even open the observatory when it's more than 10 or 11 miles an hour. But I just had to. I didn't want to lose an opportunity to show you some cool things. But the telescope has stopped moving. Now what's happening is wind is causing it to bounce. Not sure this is going to work for us. Let me try to go to 300 gain. You can see the galaxy there. Yeah, we're getting a constant buffeting of wind here. All right, well, unfortunately, this doesn't help us. But that's okay. You can try. Thanks, made everybody tired.
Sorry, excuse me.
Okay, alright, we'll try. We'll see if we can get one. Alright, let's give it a shot. We'll go 20 seconds. See if we can get a 20-second shot. I won't accept any bad images. And I don't think we're going to get them. I don't think we're going to get a good shot out of it, though. So there is the other one. It's going to look way better than that when we actually check it out and we process it. Let's oh, look at that, we got one. Let's do this. Yeah, you can see that we're probably, let's see what's going on here. Yeah, 8.05 is too high for this particular object, see? Because we're getting, so I'm going to lower this down to, let's say 7.32. And we'll clear it. Try again. And see if this will give us any clues. Mike Hedrick says, before you go, Mark, could you tell us more about what you've been up to in future TV or radio? Well, I'm still on, the proof is out there on History Channel. They're coming out the film next month for the third of 4 installments. And then that'll be an all-day affair. And then I will be at Contact in the Desert in June. I'll be at Pine Bush, as it turns out. Conference. I'll be at Ozark UFO Conference. And at all these places, I want to do a live sky tour session as well. That's part of the goal. And I'll be at Roswell as well. So that's 4 conferences so far. So it's going to be kind of cool to go to these places again. I see all my friends there, you know, all the people I've met over the years, all good people. So maybe I should just try to bring this up above 7.45. Let's do 7.49. See if that's enough to pass the test. Hello, Mr. Django. How's it going in Belgium? Yeah, don't let the screen blow over, Michael Hedrick says. Yeah, that happened because the screen belongs to Ben Hansen, a very good friend of mine. He does a night vision skywatch, and then on the heels of his skywatch, I do the SkyTour live stream, Skywatch. And he had a lot of wind. And I can't remember if that was Roswell or Palm Springs, but one of the two places. And what ended up happening was the screen blew over from the wind. It was one of those inflatable screens. Hey, we got one. Look at that. 6.8. Ooh, I like it. Look at how nice those stars look. This is Messier 33, the Triangulum Galaxy. And it's actually really beautiful. Has a lot of detail in it. Let's try to showcase some of that for you. The moon should be setting pretty soon, I think. If it's probably low to the horizon right now.
A little before local midnight.
Yeah. It's like...
I mean, if first quarter's tomorrow...
It's a couple hours away.
By definition, will shut at midnight.
Yeah. It's a couple hours off right now. Alright. Okay, so when you look at this, you'll notice right away that there's some really interesting colors. I'm going to draw those out here for you right now. Okay. So you can see there's some reds in here. Okay. You see some greens. In fact, let me just point them out. Here's a green right here. Okay, there's a green right here. There's another green down here. Oops, sorry, that's a mistake. So we have a number of interesting objects in here. Okay, this red here, this big red, this is called NGC 604. It's a gigantic star-forming region. There's another one here. There's a lot of them all throughout here. There's another little green guy right here. There's another green guy just down below here, just out of, it's in the view, but it's hidden at the moment. And you see these spiral arms coursing out from this galaxy. It's really amazing. So this galaxy has a lot of features in it that have their own names, because it's like 2.8 or 2.7 or 8 million light years away. So what you're seeing here is like 2.7 or 2.8 million years old light that's heading here. Let's scroll down a little bit, see if we can. There it is.
Moon set in Wickenburg tonight is 11:43 p.m.
Okay, so we're good. We still have it. There's another one right there. Green. What are these green patches? These green patches are supernova remnants. Remnants of stars that have blown up. Remember, our first object was the Veil Nebula, Eastern Veil Nebula? What color was it? It was green, wasn't it? And it had red in it. Well, that green is doubly ionized oxygen. All right? And that doubly ionized oxygen glows green. And maybe one night we'll talk about what are called atomic transitions, which lead to these different colors. But it can get pretty confusing, because we look at hydrogen and we say, well, ionized hydrogen looks red. Not always, okay? But the predominant transition, it's called, is for the electron to get ionized out of the atom and then come bouncing back down into the atom and end up at level 2, the N equals 2 level in the atom. There's energy levels, discrete energy levels. And those discrete energy levels are where the electrons fall into. They can't fall anywhere in between. There's only so many checkers in the checker boxes. There's only so many squares in the checkerboard they can fall into. And they can't fall in between. So that gives rise to the term quantum mechanics, discrete quanta. All right. Well, as the electron falls in, when it falls to n equals 2, it gives off a red light when it falls in. as it loses energy, it gives off energy in terms of light. And so that's exactly what we see. And although other transitions occur, the one that's predominant is the red one, which is known as hydrogen alpha. And that's what we see here in these red nebulae, and we see in the Sol Nebula. The Sol Nebula is one of these tiny red nebula that is in the Measure 33, but as seen from our own galaxy. See?
I have a question.
Yeah.
What color is hydrogen beta? It's a shade of red also, is it not?
I thought hydrogen beta was a blue, but I could be wrong.
Is it?
I had to go look. I have to go look.
I can look.
Yeah.
I've wondered. I've seen views quite a few times through hydrogen beta filters back in the day.
Yeah.
Things like the horse head and the rosette, as I recall.
Yeah. Well, remember.
And saw the Helix Nebula in hydrogen beta once.
Okay. Well, see that we lost we stacked 4, skipped 18, and so this is what our tally of good frames looks like. There's another one that's outside the scope here. I actually have a gas tube here.
You're right. It's a blue-green color.
I have a gas tube here that has hydrogen beta in it, and I use them to teach spectra classes. So it's pretty interesting. You put them in this big high voltage thing and it goes, and you see this bright color. And with the spectroscope, you see the emission lines of the hydrogen gas, and the hydrogen beta is a distinctly blue-green. It's pretty cool. So there you see, this is, again, this nebula is really pretty. This nebula, yeah, this galaxy is really pretty. And the nebulae within it are also gorgeous. Let's try to enhance the colors here a little bit. See that? Now, stars are still slightly oval. That's because I'm using a number of 7.49 rather than like a 5.8 or a 6.7 because we have a windy night. So I wanted to capture something for you. So that's what this is. That's why we're seeing it this way. All right, this is Measure 33. Okay, the Triangulum Galaxy. No, not the Yitahudi, whatever that was. All right. All right, there we are. Triangulum Galaxy, boy.
Michael Hedrick is repeating a question to you from Cosmic Ray. And Calabos has a question for you.
Let me see. Betelgeuse or Iceland? Which goes first? Oh, well, obviously Iceland, it's erupting now. So Iceland always. Because the likelihood of Betelgeuse going off is going to be dictated by the neutrino streams that we see coming from it. And so far, we don't see neutrino streams coming from Betelgeuse, so there isn't a supernova underway. At least not in the light train that's reached us so far from 700 or so light years away. But when Betelgeuse does go, it'll be visible in our daytime sky as a second star in the sky. That'll be really cool. So even if Betelgeuse is on the sunlit side of the Earth, or the sun is traveling through that region of space as we go around the Earth and we see the sun against it, as the Earth goes around the sun, I mean, well then you'll still see it in the sky. Even if it's relatively close to the sun, relatively, because obviously it's not near the sun, but you'll actually see a Betelgeuse in the daytime sky. Let's see. So, what Calibos asked now?
What do you all think about SETI recently receiving a $200 million donation recently? I don't think I'd heard about that.
Well, they just misplaced it. It was supposed to go to us. I'd love that. Well, okay, I know Seth Shostak, and I think that, it's a noble effort, noble cause. There's a lot of work to be done. And what's interesting is Seth Shostak, well, let me give you a quote from Seth, okay? He said, if there are no aliens out there, then that's miraculous. No, if there are aliens out there, then that's miraculous. If there aren't any aliens out there, that'd be a miracle. Okay, that's direct from him. So clearly, he thinks that alien life might exist out there. What he doesn't think is that they could be here, and I don't agree with him on this for reasons that I state in my lectures about dimensional travel, as we talked about earlier. So I don't think he's right on that. That's all right. We sat in a panel together, and I think it was, where were we? I think that was in Palm Springs. I think he and I at Contact in the Desert, I believe that he and I sat on the same panel. We sat next to each other. We were talking. So that was kind of an interesting interchange with Seth Shostak. Okay, we got 8 stacked here. Obviously not the best because we're getting some artifacts. Yeah. Are there other questions that I missed?
I think that was it.
Okay.
Calibos said he wanted to know what my thoughts are, I guess.
Yeah, let's hear it.
I don't really have an opinion on it.
Cop out.
Well, I've said before, somebody else famous once said, it'd be a terrible waste for all this big, beautiful universe if there was nobody there to appreciate it. And I think there is life out there. We've talked about the panspermia thing. There was something about that just recently in the news. I forget what it was now.
Okay.
Is there intelligent life? Probably. Somebody has to be first. I don't, in the fullness of time, ever since the Big Bang or whatever it is nowadays, that somebody had to have been there before us. And
I don't disagree with that.
I ultimately don't know. Will we find out during my lifetime? I hope so.
Yeah, I hope so as well. All right, well, we're going to save this here with just the 9 frames we got.
Be careful what you wish for, though. I sort of ascribe to the school of what Stephen Hawking said, that, we shouldn't be drawing attention to ourselves.
That would be great if we hadn't done it 2 billion years ago.
Oh.
As I pointed out.
Or as Ray was saying earlier, Three Stooges or I Love Lucy or stuff like that. I've talked about that before. I could just imagine some xenophobic, warlike alien species getting I Love Lucy reruns and probably declaring war on us, interstellar war.
I have a different outlook on that, and it's not because I want to believe that they're all benevolent, because they're not. I think they're indifferent, right, to us. I think they really are indifferent. But I will say this. There, that color's better. Look at that. So I'll say this. I believe that alien species out there have known we're here for as long as we've been producing oxygen in our atmosphere. And the reason is because oxygen doesn't like to stay in an atmosphere. It likes to dive into the rock strata and bond with iron compounds, for instance, of which there are many. So you get a lot of Fe2O3, rust. Mars once had a thicker atmosphere. That atmosphere was degenerated by several factors. The fact that Mars is smaller, it couldn't hold a thick atmosphere like the Earth could, for one thing. Second, Mars could have suffered a catastrophic impact that blew off tons of material, including atmosphere. Third, Mars is a smaller planet, so its magnetic field was sufficient at one time, but as the core cooled off, that magnetic field began to wane, and that meant that less magnetic field meant that less trapped high-energy particles. Ultraviolet energy could reach the ground easily, not spiral around the poles within high-energy particles, and reach the ground to cause auroras. So it meant that the Martian atmosphere was besieged by radiation it couldn't fight back against, and so water vapor that was airborne was photodisassociated, meaning that the hydrogen was torn away from the oxygens, and the oxygens were heavier and more massive atoms dropped into the ground where they bonded with iron, and the hydrogen escaped to space. So that's why Mars is red. It rusted for real and for true. So when we look at the state of planets now, we're seeing it at this stage in time, but the history of Mars shows lots and lots and lots of surface water that has run on the surface in the past. And now, because of the thinner atmosphere and the lower atmospheric pressure of like 600 pascals or whatever, okay, we're now talking about water only being able to exist as subterranean aquifers and reservoirs. One such aquifer was found under the south pole of Mars. It was like 12 kilometers long or some such thing, about a mile down. Okay, so anyway, so oxygen in our atmosphere is staying there because something's replenishing it. It's bounding. It's bounding down into the ground and bonding with iron all the time. It's part of a cycle. It's getting absorbed by the ground, but as fast as it's being absorbed by strata and compounds in the ground, it's being created by something. So we have a general balance of oxygen in our atmosphere, an overabundance, a non-natural abundance of oxygen, in fact. In fact, if you want to say it directly, our planet is in what's called disequilibrium. It's not even in equilibrium. It's out of shape. It's out of sorts. It's not in equilibrium. So the extra oxygen comes from the phytoplankton that are absorbing and creating oxygen. The oxygen is actually a waste product. So when I say you're breathing, the poop of these tiny creatures, and that's what keeps you alive, that's more than just a joke. Okay, their poop is why you're here. How's that feel? But that said, okay, the oxygen in our atmosphere then is staying at a relatively similar level throughout the millennia. And if you're a species looking for a carbon-based life like yourself, and most life in the universe is probably carbon-based, I'm a carbon bigot, then you're going to look for oxygen, because that means a stable supply of oxygen means you can have oxygen to keep you supported and your life processes going. So you'd look for oxygen. All right. So that's what it's all about, finding oxygen, and that has been happening for, as I said, over 2 billion years. So yes, the Lucy show might be, say, 75 or so years or more out into the universe. So that's 75 light years. Sure, an advanced society might have seen that, might have captured that, but an advanced society would more likely have seen the oxygen in our atmosphere long ago, millions upon billions of years before today. So it gives them a goal to shoot for, and I think that we stood out like a brilliant, blazing blue beacon in the universe, okay? And again, Carl Sagan said it best, we are a pale blue dot, right? I've said that so many times, but it is true. And that pale blue dot is a beacon to the universe. So we do stand out like a sore thumb. So Stephen Hawking said we should probably lay low, but it's too late. 2 billion years too late.
Well, I mean, detecting free oxygen and saying it's a sign of life is not the same as detecting us.
Oh, no. But detecting oxygen is detecting that there's life on a planet.
Yes, but I mean, it's not detecting humanity.
No, it's not. But it's detecting a place where a carbon-based life form might go to explore. Whether there's life there or not, they don't know. As they got closer, then maybe Lucy Carmichael will show up and they'll say, "What's this? Let's get out of here." Lucy! But still, I think that when you look at the big picture, finding life on planets is what we're looking for. We don't know what kind of life it is, but finding dimethyl sulfide, okay, on a water planet in another what's called a Hycene world, a hydrogen-rich atmosphere, is a breakthrough because it shows that maybe there's life there, because dimethyl sulfide is only produced by life. So does that mean that this water world with a predominantly hydrogen atmosphere actually has life in its oceans? The answer could be maybe. If they confirm the result, then we may have been just treated to the first evidence of life in another world by the James Webb Space Telescope. You know?
I think I'm turning into a pumpkin.
I know you are. I could tell. That's all right, though. Thank you for being here tonight, Daryl.
Sure.
Okay, Robert Thallium says, does carbonic acid from volcanoes help break bonds to release oxygen from all the oxides? Okay, that's a loaded question, right? You want to make carbonic acid, you can take a straw and blow into water. And what happens is, over a period of time, the water will turn cloudy. And that's because of the carbonic acid created by the carbon dioxide. You're seeing evidence of the carbon dioxide cycle when that happens, okay? But the carbonic acid obviously goes into the seawater, like from oxygen in the air, all right? And the oceans are what we call a carbon sink. They suck up all the carbon dioxide very, very efficiently. And so you could imagine on a planet where the climate change is so horrendous that there's a lot of carbon dioxide in the atmosphere being absorbed, then you'll acidify your oceans, all right? But as far as releasing oxygen, those are going to be other processes that are going to release oxygen, and so going that direction is not releasing oxygen per se. I don't think that I don't believe, in fact, that that's the right thought process when we talk about carbonic acid and oxygen. But we can do a chemistry class another time if you like. That's a lot of interest to me as well. All right, so the best thing to consider here is that this galaxy we're looking at right here, 2.7 million light years away or so, could be full of life for all we know. And they're looking back at us going, I wonder if there's life there too. You know? And I think that's probably true. But this is our last object for tonight. Daryl has turned into a gourd. Or a pumpkin, right? You say pumpkin, right?
Yeah, it's like Cinderella.
Oh, my gourd.
Okay.
Yeah. All right. Well, I'll save this anyway, even though it's not perfect. And we'll do this again on the very next clear night. So you guys, I hope you had a good time tonight. Let us know. Do the thumbs up. Let us know. Head up to here. Head up to skytourlive.org and check out everything we have to offer. Consider joining our Patreon. We'd love to have you. we need Patreon support in order to continue. So I'd love it if you would just consider joining our Patreon and becoming a member. A lot of people come here, watch and enjoy, and that's the extent of their support and their involvement. If you want to get involved more, well, consider that, we're trying to bring science to the world. And this is one way to do it. So thank you guys. And again, thank you to Izabela. Thank you to Robin, who also helped Izabela on this video. I think Izabela is going to be putting this out there, I think. Right, Izabela? Let me know. But we'll see. Anyway. Hey, Matthew's with us. How you doing, Matthew? Okay, well, anyway, you guys, you have a good evening, and we will talk to you, well, on the next SkyTour live stream. So you have a good evening, guys, and we'll see you later.
Good night, everybody.
Good night, everybody.